Welcome to part 2 of our lecture on motor control. This lesson focuses on the control of motor speed. In terms of controlling motors, a common requirement is to control the speed of a motor. Knowing the speed-torque characteristics of a particular motor, we can pick a point on the curve that gives us a particular speed and a particular torque. But if I have a load on the motor that I'm trying to drive, that torque is going to be fixed. So I don't necessarily want to move along this curve. What I want to do is move up and down right here. Now recall, we can shift these curves down by changing the supply voltage fed to our motor. Thus, for the same torque, I could drive the motor at 3 different speeds, omega 1, omega 2, and omega 3. And these would be based on 3 different input voltages provided to the motor. So what this tells us is not only do we require a means by which we can turn our motor on and off, we also want this motor voltage to be variable. And thus in this lesson, we'll take a look at how to implement a variable motor voltage. We're going to achieve this variable voltage using the fact that we can turn the motor on and off. Here is a PWM, or pulse width modulated signal, and the duty cycle here is roughly 75%. So 75% of each period the voltage is high or on, and 25% of each period the voltage is low or 0 volts. So here is V motor, and if we use appropriate filtering, then the voltage output should be roughly 75% or V motor. So V star here would be the duty cycle times the motor voltage. Similarly, if we have a 25% duty cycle, then V star would be approximately 25% of V motor. So here is the signal on time compared to the period, and with this in mind, we can also define now the PWM frequency, which will be 1 over the period. We need to account for this frequency along with any filtering of our signal such that we're not seeing any on-off characteristics when controlling the motor. In other words, if we want our motor to spin at a given speed, we want to make sure that our PWM frequency and any filtering that's used is providing a constant output voltage such that that motor is constantly spinning at that desired rate. Given the mechanical nature of these motors, such as the inertia that you need to overcome, what we find is that anything on the order of 100 hertz to thousands of hertz is typically appropriate in terms of the PWM frequency used to generate this variable voltage. Because this V star is an approximation of the voltage applied to our motor, we end up with a highly nonlinear curve from the duty cycle of my PWM signal to the output speed of my motor. A typical curve between duty cycle and speed at a low PWM frequency might look something like this. So here we hit our maximum speed at a 100% duty cycle. So this would be the speed corresponding to V motor. So this nonlinear behavior, this would be occurring at a fairly low PWM frequency. Now this point down here, this is going to be due to the friction torque in the motor. In fact, if the PWM duty cycle is small enough, we may never get enough current through the motor to actually get the motor started. As we increase the duty cycle, our curves will begin to flatten out, and at some point the curves start to look relatively linear. So this curve here, this will be for a high PWM frequency. So all 3 curves are at relatively low duty cycles, say maybe 18 to 20% of duty cycles. And as the PWM frequency increases, we'll find that duty cycle versus speed curve to start to look more and more linear. Now, regardless of the PWM frequency, we are still going to experience ripple in the current that is supplied to the motor. So when we send the motor voltage high, the current is going to increase, and when we send the motor voltage low, the current going to the motor is going to decrease. So within 1 PWM period, the current will be increasing and decreasing. Recall this is related to the time constants of the DC motor, specifically the inductance and the resistance. And so this ripple in the current supplied to my motor is occurring with each period of my PWM signal. So if we look at the current of the motor, we have some maximum and some minimum current And recall then that the torque generated by the motor is going to be proportional to that motor current. So we're going to end up with some torque ripple that's proportional to this current ripple. One way we could account for this torque ripple would be to increase the frequency of our PWM signal.